So in the last lecture, as part of our introduction to magnetic fields, we talked about Ampere's law. Ampere's law was a way to relate the magnetic fields that are around the outside or circumnavigating a closed surface to the total current that is passing through that surface. And we call that Ampere's law, which was related with an integral. In this lecture, we're going to be introducing a much more useful and practical form of Ampere's law in what's called the differential form. And to do that, we're going to have to introduce something called curl. So this lecture has two parts. In the first one, I'll introduce curl and talk about what it is. We're going to contrast it to divergence, which was a prior way that we looked at spatial derivatives. And then we're going to recast Ampere's law in this new form with curl. So let's start about curl and what is curl. All right, so just to remind you, we have this grad or gradient operator, which is the derivative with respect to x in the x direction plus the derivative with respect to y in the y direction plus the derivative with respect to z in the z direction. This is meaningless on its own, but you can basically apply it to things. Much like a plus sign is meaningless unless you have two things on opposite sides of the plus sign. So we consider, for example, the divergence as being the dot product of this del operator with some vector a, and that's called divergence. Divergence is a measure of the sourciness of field lines. So if you have field lines that are emerging from a given location, then that would be a positive divergence. And if you have field lines converging into a location, that would be a negative divergence. We also introduced the gradient of a scalar field, and that was called gradient. And that's basically the direction of maximum increase of that scalar. So for example, if S represents temperature, which you can define anywhere in a three-dimensional space, then the gradient of S will tell you the direction you need to go in order for the temperature to increase the fastest. All right, today we're going to introduce something called curl, which is a grad cross with some vector field. And I'm going to use H because H is going to be the magnetic field that we're going to use. And so if we take this grad operator here and we apply it with a cross product to a vector H, then we can write this as a determinant of a 3x3 matrix, where the first row is just the unit vectors x, y, and z. In the second row, we're going to put in the three components of the del operator. So this is going to be d, dx, d, dy, and d, dz. Let me stay consistent with my notation there. And in the third row, we're going to put the three components of h. So that would be the x component of h, the y component of h, and the z component of h. And we can calculate the determinant of this. If you don't have it memorized, you can certainly look it up. This is going to be the x direction, the derivative of the z component of h with respect to y, minus dhy dz, minus, in the y direction, dhz dx minus dhx dz, plus, in the z direction, dhy dx minus dhx dy. All right, so this is the definition of curl. And curl is a nice contrast to the gradient, because while gradient measures sourciness, this curl is going to define what we might call swirliness, or the degree to which field lines are rotating around a location. So this is called the curl, and it's basically a measure of swirliness. So if we have field lines rotating around a given location, then that would indicate a non-zero curl. Now the difference to divergence is that divergence was just a scalar. It's either yes, there is more field lines emerging from or diverging into. And so there was a plus or minus sign associated with the divergence, but there was no direction. And that's different when we're taking this cross product because there's also going to be a direction associated with the curl. What the direction tells us is there is an axis, and it's telling us how things are rotating around that axis. So in this case, if we have field lines that are swirling around this way, what we can do is we can use the right-hand rule, take our right fingers and swirl it in the direction that the swirling is occurring, in which case our thumb is going to point in the direction of the curl. So it's the rotation axis around which things are rotating. So that's the way the curl is defined as a direction. Now, it's worth contrasting curl and divergence, because if we have three components, we have hx, we have hy, and we have hz, and we can take the derivatives of those in each of the three different directions. So there's derivative with respect to the x direction, d dx, and there is a derivative with respect to the y direction, and the derivative with respect to the z direction. Let's just write all these out for a second. So this would be dhx dx. I'm going to go through this exercise here. And as you can certainly see, there's going to be 9 possible combinations. Whoops, I miswrote that one. That's an x right there. There's going to be 9 possible combinations, 9 possible partial derivatives that we're going to write out here. Right? Let me just d dy, d dy, d dy. All right, that should be a z. Let's correct that. All right, now finally, let's write in the coordinates. This will be hx, hy, hc, hx, hy, hc. All right, so this is a table just to show us the 9 possible ways that we can take the derivative of one component of h in one direction, or any vector field. It doesn't have to be h. All right, so there are 9 possibilities here. What you'll notice is that if we go back to the definition of divergence, right, that the divergence of h would be dhx dx plus dhy dy plus dhz dz, which is to say that the divergence is going to be sensitive to these 3 terms here on the diagonal of this little table, right? It's the partial derivative of one component with respect to its own direction. If you take a look at that definition of curl that we came up over here, you'll notice that all of the partial derivatives have a different coordinate on the component as we have the direction. This is z and y, this is y and z, this is z and x. They're all different, which means that for the curl, for the curl, we are basically using the other 6 components of this partial derivative. So in that sense, curl and divergence are very much sort of opposite each other, in that they are sensitive to different aspects of the way a vector field might evolve and might change as a function of direction. And that should sort of make sense, because if we think about the notion of field lines emerging from a certain location, that is precisely the opposite of things swirling. There's no swirling that's happening here, right? There's no swirling, there's just emerging. Whereas if we have some swirling happening, then nothing is emerging or converging into the location. They're very much opposites of each other. All right, so that's this notion of curl, that it's a nice way to measure the degree to which things swirl around. And that should make sense, because if we think about Gauss's law, sorry, not Gauss's law, but Ampere's law, we should be able to relate that, because we had this sort of surface right here, and we had this notion that if there are currents that are running through this surface, it's going to create magnetic fields that sort of loop around this surface, and that seems to fit curl very well. In the next video piece, we're going to take a look a little bit closer and sort of redefine Ampere's law.